In this video, we're going to talk about the concept of work. This will be our last application of integrals, and we'll move on to other topics. So the work W that a constant force F does when moving an object over a distance d is defined to be W equals F times d. Now in that definition, you need the force to be constant. The unit of work is the unit of force times the unit of distance, so that's either measured in, usually in newtons, whenever you have your distance, when the force is measured in newtons and the distance is measured in meters, the unit of work is the Newton meter, which is also called a joule. And if the force is measured in pounds and the distance in feet, you have just foot pounds, and there's no special name for that. So we'll use either joules or we'll use foot pounds. If the force is not a constant, then calculating work becomes more complicated. So the idea is to, let's say we have the force given by some sort of function, capital F of x, where x is the position of the object. So as the position changes, the force changes. We want to find the work done to move the object from x equals a to x equals b. So we're going to divide the interval from a to b into smaller subintervals, n equals subintervals of equal width. The width we'll call delta x. If we choose a point x sub I from the ith subinterval, then we're going to take capital F of x sub I as an approximation for the force on that subinterval. So we're going to treat the force as constant on each of these small subintervals. And in that case, if the force is constant, then the work is force times distance. The force is F of x sub I, and the distance is delta x, the width of the interval. And it's approximation because the force is probably not exactly constant, but if the interval is small enough, it's probably a good approximation. To get the total work done, we add up those approximations for all the intervals, and of course, to make the approximation better, we increase the number of subintervals. We take the limit as the number of subintervals goes to infinity, and it's a Riemann sum, so we get an integral, and this is the final result. The work that this force does, moving an object from x equals a to x equals b, is the integral from a to b of the force function. The hard part of this problem is usually figuring out what that force function is, depending on the physical situation. So here's an example of that using springs. So there is a relationship between force and distance of a spring, and that's given by what's called Hooke's law. The force required to hold a stretched or compressed spring a distance of x units from its natural length is some constant k times x, where k is a positive constant which depends on the nature of the spring. Now this law holds as long as you don't stretch the spring too far. If you stretch it too far, you will kind of break the spring, and it doesn't apply anymore. But as long as you don't go too far from the natural length, and you're not, destroying the metal or bending or twisting or whatever might happen to it if you stretch it too far, then this law is pretty good. So we have a force function, and so we were able to find work done in stretching or compressing a string. Notice here in Hooke's law that the distance x is the distance from the natural length of the spring. So if you don't apply any force, the spring is however many units long, and x tells you how far you've stretched it or compressed it from that natural length. So it's not the actual length of the spring. Alright, let's do an example. So let's say we have a spring whose natural length is 5 meters, and we know from testing it that its spring constant k is 30 newtons per meter, and we're going to stretch it 10 meters from its natural length. How much work do we do to do that? Well, here's the answer. So the force is k times x, where k here is 30 and x is whatever, the distance we've moved it. So 30 times x is the force function. Now x is the distance we've moved from the natural length. So I want to stretch this 10 meters from the natural length, so I start at 0 from the natural length, and I go till 10 from the natural length. That's what I need to integrate. Okay, even though you start out with this thing 5 meters long, you don't go from 5 to 15, you go from 0 to 10. Okay, and the answer here happens to be 1500, and this is in newtons and meters, so the units here is joules. And there's the integral if you want to do it, though it's not a hard integral. Alright, here's another example. Let's say a spring has a natural length of 20 centimeters, and a 40 Newton force is required to stretch and hold the spring at a length of 30 centimeters. How much work is done in stretching the spring from 35 to 38 centimeters? Okay, now to do this work, we're going to integrate the force function. To do the force function, we need to know the spring constant, K. And I didn't tell you that, but I did give you enough information to find it, because I told you how much force is required, 40 newtons, to get from the natural length of 20 to the length of 30. That information allows you to compute the spring constant, and once you have the spring constant, then you can compute the work in this other situation. Now notice here that I gave you these distances in centimeters. We're going to work in newtons, and with joules, I want my distances to be measured in meters. So I'm going to convert all those things to meters. Make sure everything is in newtons and in meters when you want to work with joules. Okay, so let's find the K first. So remember, the formula is F equals Kx. So I told you F is 40. K is what we're trying to find. What is X? X is the distance from the natural to however far we stretched it with 40 newtons. So that's the distance from 20 centimeters to 30 centimeters, which is 10 centimeters, or 0.1 meters. So 40 newtons goes with 0.1 meters. So 40 newtons equals K times 0.1. Divide both sides by 0.1, and you get K is 400. So now that we have K, we can integrate 400 times X. What's the limits of integration? Well, I want to move it from 35 to 38. Remember, we need to do two things. One, convert those to meters, and second, convert those to distance from the natural length. Okay, the absolute length we don't care about. When using Hooke's law, we need the distance from natural. So the natural length is 20, so that's 15 centimeters from natural, which is 0.15 meters. This is 18 centimeters, or 0.18 meters from the natural length. That's what our limits of integration need to be. 0.15 meters from the natural length stretched to 0.18 meters from the natural length, and the force function is 400x. And this turns out to be almost 2 joules. Alright, here's another example. This doesn't have to do with springs. So let's say we have a cable that weighs 2 pounds per foot. It's attached to a bucket that's filled with coal that weighs 800 pounds. How much work in foot-pounds does it take to raise the bucket from the bottom of a 500-foot mine shaft? Alright, in this case, the force involved is the weight. And there's two weights involved. There's the weight of the bucket with the coal, that's 800 pounds. That's a constant. And if that's the only weight we had to worry about, then we would just have a constant 800 pounds being raised up 500 feet, and we do 800 times 500, that'd be it. But we also have this cable, and if you're going to have 2 pounds per foot of cable, and this cable is going to reach down 500 feet, then that means you got 1,000 pounds of cable dangling down there, which, you know, compared to 800-pound bucket, that's not negligible. So we shouldn't ignore the weight of the cable. The problem is that the weight of the cable changes. We're not just going to, you know, it's not like you grab on the end of the cable and you haul that end up 500 feet up into the air. The idea is you're going to roll this cable up, you know, on like some sort of drum or something. And so the weight of cable that's dangling out there is getting less. As you roll this cable up, there's less cable out there that you have to lift now. So the force changes. The weight gets smaller as you raise it because there's less cable out there. Okay, so let's call X how much cable is left, and that means the force is 2 times X. Remember, the cable is 2 pounds per foot. If we have X feet left, then 2 times X is the weight of the cable, and then plus the bucket and the coal is 800. So 2x plus 800 is the force. That's the function we want to integrate. What's the limits of integration here? Well, we're going to go, we need to go from 500 feet remaining when it's all stretched out at the beginning to when there's no cable remaining, we have it all rolled up and we've raised the bucket the whole way. So 0 to 500. Okay, and then I know this looks kind of upside down because it starts out at 500 and stops at 0. Don't think about this chronologically. If you do 500 to 0 here, you'll get a negative work, which is not what you want. So 0 to 500, those are our boundaries. Here's the integral in Sage, 650,000 foot-pounds. Okay, here's our final and most complicated example. A tank has the shape of an inverted circular cone. So here's a cone with a circle base, and it's inverted, it's upside down. So this is a water tank. Has a height of 15 feet, so 15 feet there. It has a base radius of 4 feet, so here's 4 feet is the radius there. It's filled with water to a depth of 12 feet. So imagine here a little water at 12 feet, which I didn't draw in the picture. So water is filling up this cone. I want to find how much work I need to do to get all the water to the top of the tank. Okay, I'm going to put a little pump, and it's not that the pump is down here at the bottom and the water is raised the entire 15 feet. I want to think of the pump kind of floating in the water, so I'm going to take this, if this is 12 feet right here, the beginning water level, that level of water has to go up 3 feet. And down here, if this is, maybe this is 5 feet, that's got to go up 10 feet. And down here at the very bottom, this little bit of water has to go up the whole 15. So the amount you need to raise it changes depending on where you are in this tank. Now the force also changes as you move around, because the force is provided by the weight of the water. Since this is a cone, there is more water up here at the upper levels than down here, and so the weight is more. So you got lots of weight needs to raise a small distance, and a little weight needs to raise a further distance, and so we'll figure out how that's going to work out. Now to do this, we need this density of water, roughly 62.4 pounds per cubic foot. So we're going to figure out the volume of water that we have at a given level in cubic feet. We'll multiply it by this and get the pounds. Pounds is the weight, that's the force. Okay, well, can't find a simple force function in this one because it's kind of more complicated. So we're going to have to go and figure out our integral from scratch. So let x be the vertical distance from the bottom of the tank. So the bottom of the tank will be x equals 0. The top of the tank will be x equals 15. And the water goes from 0 until 12 at the beginning until we start pumping it out. So we're going to divide this interval from 0 to 12 into 12 equal subintervals of width delta x. Did I say n equal subintervals of width delta x? Anyway, okay. We're going to choose a point in the ith subinterval. For that subinterval, we're going to approximate the water in that subinterval with a cylinder of radius ri. Now really it's not a cylinder, it's a frustum of a cone. I'm not going to worry about getting the shape exactly right. More complicated than I need to be. I think as we take the limit as n goes to infinity, this cylinder will be good enough of approximation. So here is x sub I, goes from the bottom up until this point. Here's r sub I is the radius there. Okay, this is just a cross section of the cone. So 15 feet all the way up, 4 at the base, r sub I at the ith subinterval. So you're going to imagine here I got a little cylinder of water right here. I want to find the volume of that cylinder. Okay, now to find the volume of that little cylinder of water, what do I need? Well, the volume of the cylinder of water is pi radius squared. That's the area of the base of the cylinder, and then multiplied by the height. The height is delta x. Okay, that's the width of my subinterval. So delta x is the height. What I need to know is what is this radius in terms of x. Okay, I'm going to integrate in the x direction. My sum here, I'm going to build a Riemann sum to get an integral. I need this sum to be based on x. So when I take the limit, I'll get an integral in the x direction. So that means I need to know the volume here in terms of x. And right now I know the volume in terms of r. So I need to figure out how r is related to x. The way I'm going to do that is with similar triangles. Okay, this big triangle here, the 15, and here's the hypotenuse and the 4. That big triangle and the small one, xi, hypotenuse, and then r sub I. Those two triangles are similar because they share this angle here. That means that the ratio of corresponding sides are the same. So if I take the ratio of this little leg to this long leg, r to x, that's the same as the ratio of 4 to 15. Alright, so this is what we get from geometry with the similar triangles. Multiply both sides by the x sub I, and you get r sub I is 4/15 of x sub I. Alright, now we know r. The force is provided by the weight of the water, which is this density here, 62.4 pounds per cubic foot, times the volume in cubic feet. So what's the volume? The volume of my ith subinterval of water is approximately the volume of a cylinder of water. Okay, it's not exactly a cylinder, it's a piece of a cone, but approximately the cylinder, which is pi r squared h. R is given by r sub I, h is given by delta x. I'm going to replace r sub I with 4/15 x sub I, which I just figured out above. That's what r sub I is. So the force, which is the weight of the water, is, for the ith subinterval, is 62.4 times the volume, which is roughly 62.4 times this mess we got up here. And I'll do a little simplifying. 62.4 times 4/15 gives me this fraction here. So the force on the ith subinterval is approximately this mess here. The distance required to get from that ith subinterval to the top of the tank, remember we want to figure out the work to get to the top. So I'm going to take that ith subinterval, I'm going to lift it up to the top at 15. I'll call that d sub I. That distance is 15 minus x sub I. Okay, remember x sub I is the distance from the bottom up until my ith subinterval. Roughly, x sub I is a point in the ith subinterval. So the ith subinterval actually takes up a little bit of space, but that's okay. So the work required is force times distance. So it's approximately, here's the force, which is the weight. Here's the distance, which is the 15 minus x sub I. The total work required then is approximately the sum of all the works for the ith subinterval, which is approximately this sum. Okay, and to get the actual work, we take the limit as n goes to infinity. Now, this is a Riemann sum. Notice this is not a Riemann sum of the force function. The force function is just this part. But then we got this extra part with the distance. So this is not quite as simple as the other examples we did. But this is a Riemann sum. So when you take the limit as n goes to infinity, you get an integral. Now, what's the limits of integration? Well, the water ranges from x equals 0 to x equals 12. So that's where we need to integrate. Okay, we don't have any water between 12 and 15. So there's no work done there. That's empty. So the water goes from 0 to 12. As I take the limit as n goes to infinity, these x sub i's become x, and the delta x becomes dx, as that we've seen multiple times with Riemann sums becoming integrals. So this is the integral we need. Here I did it down in Sage, though this is a polynomial, so it's not that bad to do by hand. So roughly 48,000 foot-pounds of work required for that. Okay, in your assignment, I will give you one that involves pumping water from a tank, but it won't be quite so complicated. I won't give you a cone. I'll just give you a cylinder, so you don't have to worry about this changing radius. So it'll be a little simpler, but you'll still have to kind of follow this example. All right, so that's work. That's the end of our applications of integrals. We'll move on to another topic next time.